In our last exploration, we discovered the terrifying truth. The universe is not just expanding, it's accelerating. Dark energy, a mysterious force that makes up 68% of everything, is pushing space apart faster and faster. Galaxies are fleeing beyond cosmic horizons, never to be seen again. The universe is racing toward heat death, an eternal emptiness where nothing can ever happen. But we left with haunting questions. What is dark energy, really? Why does it have the value it does? And what is this empty space that's expanding? Today, we dive into the quantum void. Because if dark energy truly is a property of empty space, then understanding it requires understanding what empty really means at the most fundamental level. And what we'll discover is more unsettling than the expansion itself. Empty space is not empty. The void is not void. And the nothingness between galaxies might be the most active, dangerous, and mysterious entity in all of existence. While astronomers mapped the expanding cosmos, theoretical physicists dove deeper into the quantum nature of the vacuum itself, because in the quantum world, nothing is ever truly at rest. Even in a perfect vacuum, devoid of any particles or radiation, quantum fields fluctuate wildly. These are not mere mathematical abstractions. These fluctuations have real, measurable consequences. They affect the behavior of atoms, they shift energy levels, they can even be detected in laboratory experiments. The most famous demonstration of vacuum fluctuations is the Casimir Effect, discovered in 1948. If you place two uncharged metal plates very close together in a vacuum, they experience a tiny attractive force. This force arises because the quantum fluctuations between the plates are restricted compared to the fluctuations outside them. The vacuum itself is pushing the plates together. This proved that the vacuum has structure. It's not empty nothingness. It's a seething ocean of quantum possibilities, with virtual particles constantly appearing and disappearing, borrowing energy from the vacuum and repaying it before they can be detected directly. Each quantum field contributes to this activity. The photon field creates virtual photons. The electron field creates virtual electron-positron pairs. Even the Higgs field, responsible for giving particles mass, fluctuates and contributes to the vacuum's energy. Now, here's the crucial question. If each quantum field has a minimum energy associated with these fluctuations, and if there are many quantum fields in nature, shouldn't the total vacuum energy be enormous? When you try to calculate this energy, you encounter infinities. The fluctuations at shorter and shorter wavelengths contribute more and more energy with no apparent limit. Physicists deal with this by introducing a cutoff energy scale beyond which the calculations no longer apply. Perhaps quantum field theory breaks down at the Planck scale, where quantum effects and gravity become equally important. Even with a reasonable cutoff at the Planck energy, the predicted vacuum energy is about 10 to the power of 113 joules per cubic meter. The observed dark energy corresponds to about 6 times 10 to the negative 10th joules per cubic meter. The theory predicts a number with 123 digits. Observation gives us a decimal point followed by 9 zeros and then a 6. The mismatch is so extreme, it suggests we're not just slightly wrong, we're fundamentally misunderstanding something about reality. This is the cosmological constant problem, the worst prediction in all of physics, and it sits at the heart of dark energy. Some physicists have argued that there must be a hidden symmetry that cancels out all the vacuum energy contributions, forcing the total to be exactly zero. The most promising candidate was supersymmetry, a proposed symmetry that relates particles of different spin. In supersymmetric theories, for every ordinary particle, there's a superpartner with opposite quantum statistics. The vacuum energy contributions from particles and their superpartners would cancel out precisely. This was an elegant solution, too elegant, as it turned out. Experiments at the Large Hadron Collider searched for supersymmetric particles and found nothing. If supersymmetry exists, it's broken at energy scales we can currently access, And broken supersymmetry doesn't solve the cosmological constant problem. The quantum vacuum also raised another disturbing possibility. What if the vacuum we observe is not in its lowest energy state? What if it's in a false vacuum, temporarily stable, but not truly stable? In quantum field theory, fields can have multiple stable states, like a ball that could rest in several valleys of varying depth. The lowest valley represents the true vacuum, the state of minimum energy. But a field could get trapped in a higher valley, a false vacuum, separated from the true vacuum by an energy barrier. If our universe exists in a false vacuum, it could spontaneously tunnel through the barrier to the true vacuum state. This process would start at a random point in space and expand outward at the speed of light, like a bubble of new vacuum growing in the old vacuum. Inside the bubble, the laws of physics might be completely different. Particles might have different masses, forces might have different strengths. The universe as we know it would cease to exist. This is called vacuum decay, and it's one of the most terrifying scenarios in all of physics. There would be no warning. The bubble of new vacuum would approach at light speed, meaning we couldn't see it coming. One moment, the universe would exist. The next moment, everything would be rewritten at the most fundamental level. Is this likely? We don't know. We can't calculate the lifetime of a false vacuum without knowing the exact shape of the potential energy, which we don't. The current vacuum might be perfectly stable, or it might decay tomorrow, or it might take longer than the current age of the universe by a factor of trillions of trillions. Some physicists have argued that the discovery of dark energy might actually increase the risk of vacuum decay. If dark energy represents the energy density of our current vacuum state, and if there's a lower energy state available, the transition between them might release enough energy to accelerate the expansion dramatically, perhaps triggering a cascade of vacuum decay events. But this is highly speculative. The connection between dark energy and vacuum stability is not well understood. What's not speculative is the deep connection between quantum mechanics and the structure of space-time. Quantum field theory treats space-time as a fixed background on which fields evolve. General relativity treats space-time as a dynamic entity shaped by matter and energy. These two descriptions are fundamentally incompatible. At ordinary energies and scales, the incompatibility doesn't matter. Quantum effects are important for particles. Gravitational effects are important for planets and stars. The two domains rarely overlap, but at extreme conditions, like near black hole singularities or at the moment of the Big Bang, both quantum mechanics and gravity become crucial, and our theories break down. This is the realm of quantum gravity, and it's the frontier of theoretical physics. Some approaches suggest radical ideas about the nature of space and time. Perhaps space-time is not fundamental, but emerges from something deeper. Perhaps at the smallest scales, space and time are discrete, quantized, made of tiny, indivisible units. Perhaps what we call expansion is really information diffusing through a network of quantum entanglement. These ideas might seem abstract, but they could be crucial for understanding dark energy. If space-time is emergent, then the expansion of space might be a thermodynamic phenomenon, similar to how temperature emerges from molecular motion. The universe might be expanding because that's the natural state of maximum entropy for the underlying quantum structure. The quantum vacuum holds many secrets. It's the stage on which all of reality plays out. It's the source of virtual particles, of forces, possibly of space-time itself, and it might be the key to understanding why the universe is expanding into nothing. Somewhere in the mathematics of quantum fields, in the fluctuations of the vacuum, in the entanglement of invisible degrees of freedom, lies the answer to dark energy. We haven't found it yet. We might not find it for decades or centuries, but the vacuum is trying to tell us something, and that secret might be this: nothing is more fundamental than something. The void is not passive, it's active, creative, relentless, and it's winning. Mapping the void. While physicists struggled with the theoretical implications of dark energy, astronomers set out to map the expanding universe in unprecedented detail. If we couldn't understand why the universe was accelerating, perhaps we could at least measure exactly how it was accelerating. The Hubble Space Telescope played a crucial role in this endeavor. Launched in 1990, it could observe distant galaxies with unprecedented clarity, free from the blurring effects of Earth's atmosphere. Deep field images revealed galaxies billions of light years away, showing the universe as it was when it was just a fraction of its current age. These observations revealed something profound. The early universe looked different. Galaxies were smaller, more chaotic, less organized. The cosmic web was just beginning to form. Over billions of years, gravity had pulled matter together into ever larger structures, while dark energy resisted, creating the vast voids we see today. By comparing the distribution of galaxies at different epochs, astronomers could trace how the tug-of-war between gravity and dark energy had evolved over cosmic history. In the early universe, matter dominated. Gravity pulled things together, forming the first stars and galaxies. But as the universe expanded, the density of matter decreased, while the density of dark energy remained constant. Eventually, around 4 billion years ago, dark energy began to dominate, and the expansion began to accelerate. This transition point is crucial. It's when the universe's fate was sealed. Before that transition, the expansion might have eventually slowed or even reversed. After it, acceleration became inevitable. The Wilkinson Microwave Anisotropy Probe, launched in 2001, spent 9 years measuring tiny temperature variations in the cosmic microwave background with unprecedented precision. These temperature variations, just a few millionths of a degree, represent density fluctuations in the early universe. The WMAP data confirmed that the universe is spatially flat, meaning its overall geometry is Euclidean rather than curved. This was predicted by inflation theory. The data also pinned down the cosmic composition with remarkable accuracy. About 5% ordinary matter, 27% dark matter, and 68% dark energy. But here's where things got strange. When astronomers measured the Hubble constant using nearby supernovae and other local distance indicators, they got a different answer, about 73 kilometers per second per megaparsec. The two measurements disagreed by far more than their estimated uncertainties. This became known as the Hubble Tension, and it's one of the most perplexing problems in modern cosmology. Either there's some systematic error we haven't accounted for in one or both measurements, or there's something wrong with our cosmological model, some new physics operating between the early universe and today that we haven't recognized. Meanwhile, ground-based surveys began mapping billions of galaxies across vast swaths of sky. The Dark Energy Survey used a specially designed telescope in Chile to measure the positions and redshifts of hundreds of millions of galaxies, tracing how cosmic structure evolved under the influence of dark energy. These surveys employed a technique called weak gravitational lensing. As light from distant galaxies travels through the universe, its path is bent by the gravitational fields of intervening matter, both ordinary and dark. By measuring how galaxy images are slightly distorted, astronomers can map the distribution of all matter. The results were remarkable. The universe's large-scale structure matched theoretical predictions remarkably well, assuming the existence of dark matter and dark energy. The cosmic web was real, and its properties encoded the history of cosmic expansion. But with each new measurement, the mystery of dark energy remained as opaque as ever. We could measure its effects with increasing precision. We could map how it influenced the growth of structure. We could trace its dominance over cosmic history, but we couldn't determine what it actually was. Some of the most intriguing observations came from studying not galaxies, but the vast voids between them. These cosmic voids, hundreds of millions of light years across, are the largest structures in the universe. They're not completely empty, but they contain far fewer galaxies than average regions of space. The voids are expanding faster than the average expansion rate because there's less matter to slow them down. By studying how voids grow over time, astronomers can measure the strength of dark energy and how it competes with gravity. The observations confirmed that dark energy is winning. The voids are growing relentlessly. There's something eerie about these voids. They represent the future of the universe writ large. As dark energy continues to dominate, more and more of the cosmos will resemble these empty regions. Space itself
seems eager to become nothing. As these mapping efforts continued, physicists began to quantify the nothingness itself. Empty space, according to our measurements, has an energy density of about 6 times 10 to the negative 10th joules per cubic meter. That's almost nothing. A cubic meter of vacuum contains less energy than a few grains of sand. And yet, that tiny amount of energy, multiplied across the vast volume of the universe, dominates everything. There's so much empty space that its collective energy outweighs all the matter and radiation combined. The nothing is more powerful than the something. The mapping of cosmic expansion revealed how delicate the cosmic balance is. If dark energy were slightly stronger, it would have dominated earlier in cosmic history, preventing galaxies from forming. If it were slightly weaker, the universe might have recollapsed before stars could ignite. The fact that dark energy has just the right strength to allow for structure formation and then to become dominant afterward seems like an extraordinary coincidence. Unless it's not a coincidence. Unless there are many universes with different values of dark energy, and we inevitably find ourselves in one where the value allows for our existence. This is the heart of the anthropic argument. But this raises a troubling question. If the properties of dark energy are essentially random, determined by some cosmic lottery, then physics has reached its limit. We can never truly explain why dark energy has the value it does.
As we've explored the accelerating expansion and the quantum vacuum, we've glimpsed a concept that appears again and again, the horizon. Not the horizon you see when looking at the ocean, but something far more profound, the cosmic event horizon, the boundary beyond which we can never know anything, no matter how long we wait or how powerful our telescopes become. This horizon is not a physical barrier. It's a consequence of the expansion of space combined with the finite speed of light, and it's shrinking. Right now, the observable universe has a radius of about 46 billion light years, but the observable universe is not the same as the universe we can potentially observe. Due to the acceleration, there are galaxies that we can see today whose future light will never reach us. They are receding so quickly that light emitted from them now is being carried away faster than it can approach us. This defines the cosmic event horizon. It's currently at a distance of about 16 billion light years. Any galaxy beyond this distance will eventually fade from view and never be seen again, no matter how long we wait. And here's the crucial point. This horizon is getting closer, not in physical distance, but in the sense that more and more galaxies are crossing it. The observable universe will eventually shrink to include only our local gravitational neighborhood. In about 100 billion years, all galaxies outside our local group will have crossed the event horizon. An astronomer in that distant era would see only the merged remnant of the Milky Way and Andromeda galaxies, along with a few smaller satellites. The rest of the universe would be completely dark. That future astronomer might conclude that the universe consists of one island galaxy surrounded by infinite empty space. They would have no evidence of the Big Bang, no evidence of cosmic expansion. The history of the universe would be erased by the expansion itself. This raises a disturbing question. What if we're already in that situation? What if there are phenomena beyond our current horizon that would completely change our understanding of reality? The horizon also has thermodynamic implications. Some physicists have suggested that the cosmic horizon has entropy and that this entropy is related to dark energy. In this view, dark energy might be a manifestation of the universe's attempt to maximize its entropy. The expansion increases the area of the cosmic horizon, which increases the entropy. The horizon connects to the holographic principle, one of the strangest ideas in modern physics. The holographic principle suggests that all the information contained in a volume of space can be encoded on its boundary surface. If this principle applies to the universe as a whole, then all the information about our observable universe might be encoded on the cosmic event horizon. The horizon is closing. The universe is becoming unknowable, and we can only watch as galaxy after galaxy slip beyond reach.
taking their secrets with them into the eternal void. We've now mapped the expanding void. We've measured dark energy's dominance. We've traced how galaxies form and dissolve under its influence. We've confronted the shrinking horizon that will eventually isolate us from the rest of the cosmos. But knowing these facts brings us to an even deeper question. What does all of this mean for the ultimate fate of the universe? If the expansion continues accelerating, where does it lead? In our next journey, we'll explore the architecture of doom, the various scenarios for how the universe might end, heat death, where everything fades into eternal darkness, the big rip, where acceleration becomes so extreme that it tears apart atoms themselves, and the possibility of cyclic universes, eternal return, and escape from cosmic fate. We've discovered that dark energy exists. We've measured its effects. Now we must confront what it means for the end of everything, for the death not just of stars and galaxies, but of possibility itself. The void is patient, but its appetite is infinite, and we're beginning to understand what it's truly hungry for. To be continued in Part 3, The Architecture of Doom, where we explore the ultimate fate of the universe, heat death, the big rip, and the possibility of cyclic universes, eternal return, and escape from cosmic fate.